Kazu Miyazaki, and then a team of people helping us organize it. But I'm going to throw it over to Susan Owen, who is the co-lead for the whole SUDS initiative, of which the seminar series is just one little bit of it. Susan has been at JPL for 18 years, started out in Section 335, working on using GPS to constrain earthquake and volcano models. She is currently the section manager for Earth Sciences and the deputy project scientist for NICER. And I will pass that off to Susan now.
Great, thank you, Daniel. Welcome. So welcome everybody to our first in the series of the SUDS seminars. I'm just going to give a quick overview of SUDS and then pass it off to our speaker for today, Lukas Mandrake. So just really briefly, SUDS, which stands for Scientific Understanding from Data Science, is a project that is going to be going on for 3 years that is meant to form a community of practice between the physical sciences and the people working on data science, to increase the speed, depth, and rigor of scientific return by revealing new connections through data science. And data science here we're referring to as model-based inference, uncertainty quantification, and machine learning. So we're really trying to bring together these 6 communities, and we're seeing that some of the really exciting advances are going to be coming from the integration of these 3 different types of data science approaches. And today we're going to be hearing about an overview of just some of the ways in which these approaches can directly help the physical science researcher. At a glance, this effort to build the SUDS community of practice consists of a council that is in charge of strategic planning and oversight. Lukas and I lead the council, and then many different working groups led by members of the community to help with education and training opportunities, community support services, and outreach and engagement. Included in this are 3 strategic initiatives that span the 3 different areas of physical science: Earth, astrophysics, and planetary. So we're very excited to be kicking off some of these events. We had our first physical science short course yesterday, and our seminar is starting today. And our inaugural speaker for our seminar is our very own Dr. Lukas Mandrake. He's been at JPL since 2002, and his research efforts include enabling new missions through onboard science autonomy, revealing subtle relationships through the interpretable machine learning, and raising the standards of practice for JPL data science. He's currently the supervisor for the Machine Learning and Instrument Autonomy Group, as well as the Machine Learning and Science Autonomy Strategic Lead for the Information and Data Science program. And it's been great working with him as the co-lead for this SUDS effort. So with that, I will pass it off to Lukas. Lukas, take it away.
Okay, everybody, hopefully that looks good to you. Today, we're going to be talking about an overview of data science for physical scientists. Welcome to our first SUDS seminar. Please hold verbal questions until the end, but feel free to engage the chat in a lively way by posting questions or answering those you can. I'll also engage questions at the end. Today's talk is intended to build understanding between physical scientists and data scientists to help them come together and more efficiently communicate project goals, and to help set standards for data scientists seeking to contribute to the SUDS community. Each of these topics is worth a talk on its own. First, we'll discuss the data challenge that lay before physical science advancement and how it extends beyond merely big data. Next, we'll spend some time defining and differentiating useful data science nomenclature and concepts, especially those that arise when using data science to further understanding and insight. Finally, we'll walk through a tour of the capabilities that data science brings to physical science, along with the common patterns and workflows that enable them. As we go, keep in mind that many of the new capabilities involve the use of machine learning. Even though they involve the use of machine learning, the translation back to physical insight often requires uncertainty awareness and occurs in the presence of and directly informs existing inference-based physical models. So what's the big deal with modern science data, and why is today different than a decade ago? A recent paper summed up the challenge nicely by stating, the ability to collect and create observational data far outpaces the ability to assimilate it sensibly, let alone understand it. Our story centers on the most precious and limited resource of all, an analyst's time spent ingesting and understanding. These are just notional graphs to make a point. What they show is that centuries ago, a physical scientist had to spend a great deal of their time in the physical act of making manual measurements and writing them down, as shown in blue. Then they engaged in manual data calculation, preparation, and reduction in red. Further time was spent comparing with theoretical prediction in green, leaving only a small amount of precious brain power to try and understand the results in purple. The goal, as always, is a process level understanding that is verified by the ability to make statistically valid predictions. As the years pass, the advent of electrical sensors and meters reduced the human effort required to take measurements. Mechanical and then digital calculators removed the bottleneck of data processing. By removing those limitations, scientists were free to spend much more of their effort towards elaborate theory-driven computer models and derive new levels of understanding by comparing them to observation. The rise of data science in this lens is about reducing the effort required to model and explore data, leaving the most time to focus on discovery and understanding. And quite a lot of data there is. We have all heard of data science and machine learning in the news in the context of big industry. I'd like to walk you through just one example of what industrial big data problems can be like. In the 90s, an insurance company named Geico decided that its customers didn't want personal relationships with insurance brokers anymore. They wanted to relate to insurance as a commodity that could be easily purchased online with a minimal wait. This concept of the instant insurance quote is essentially a statistical estimate of how risky a driver you are. So how can we estimate that for anyone with minimal information in 15 minutes or less? To solve this problem, they made two assumptions. Past performance predicts future behavior, and risky people tend to be connected to other risky people. So if you know some people's history and how everyone's connected, say by mining the newly emerged internet, they can just invert that very sparse terabyte matrix every week for every insurable driver in America, just in case you click. When you put in your information into Geico's website to get a quote, you aren't providing them information to judge your risk. You're just identifying yourself. They already know if they trust you. These simple ideas resulted in a $32 billion company. The data science approach used here is valid, it's interesting, and it certainly has its own technical challenges and sophisticated tools. So is this the same sort of thing that science needs? Well, we've all seen graphs like this before, a nice exponential curve showing the immense data volumes being generated and consumed by humanity, in this case in the zettabytes. And the small subset of this data that represents Earth science observations has a similar exponential dependence. There's the big data challenge. But let's probe deeper into the character of these data domains. Most human and industrial data is fairly intuitive. That is, it is often reducible to human understandable processes like clicks on a website, photos of a place, or emails. However, it's also often undisciplined, approximate, and haphazardly collected in time and space. The goals of analyzing this intuitive but messy data are often for general decision guidance, like which ad to put in front of you or how much to price a commodity. Science data is radically different. It's fractally complex, like nature itself. The more you attempt to zoom in and explain it, the more processes and details you find. It's precise, calibrated, standardized, and when possible, densely and uniformly sampled in space and time. We do this because, hard as it may be, reducing the data to a process level understanding is the point of the venture. We control what variability we can to ease the analysis of what remains. So what is uniquely difficult about modern science data analysis beyond scaling up our existing analysis to the big data regime? For example, let's take a mere 50 megabyte science data set, hardly worth mentioning in the big data regime, and say it contains spectral observations of the Earth's surface. There's that fractal complexity element already, with each observation simultaneously observing hundreds or thousands of individual wavelengths. But wait, the spectra are also spatially correlated. To form valid conclusions, they should be jointly analyzed in relevant groupings. And in fact, there are multiple observations in each location at different times. And rather than simply mine out high-level decision support like, where might I like to vacation, my goals sound more like this. With respect to my existing theoretical and empirical understanding of this system, augmented by computational methods, can I reduce these observations into currently known processes, identify phenomenon of interest, recognize new or emergent phenomenon, and finally, can I advance my understanding? All that in 50 megabytes. This isn't big data. This is big complexity. The challenges involving in transforming today's science data into insight are threefold. The big data story is there, of course. For example, some astronomy datasets have already reached scales where it is unlikely that any one image in a collection will ever be reviewed by a human due to insufficient available scientists and grad students. How to draw valid, consistent conclusions from and discover new phenomenon in such massive datasets requires new methods. And as we saw, it's more than volume. It's complexity. In Earth science, for example, multiple data records must often be harmonized and considered simultaneously. This requires a human analyst to consider dozens or hundreds of relevant variables at the same time, while the resulting curse of high dimensionality restricts and conceals valid conclusions. And the fine spatial and temporal resolution of modern records, while providing unprecedented process insight, requires careful handling of the spatio-temporal correlations, because the observations are no longer independent and must be considered jointly. Our physical models, meanwhile, have grown massive and hungry for computation at scales that challenge even cloud computing. When they disagree with observation, identifying what's wrong or missing in these complex, coupled, multi-scale systems has become its own challenge. So despite our progress in gathering spectacular data sets, it has never before been easier to miss a vital signal or hallucinate a false conclusion. The kinds of data science that address these challenges benefits from and leverages the powerful tools that academia and industry have developed. But the approaches that facilitate research are often very different and form their own specialization. By now, I hope to have motivated the considerable challenges that lay before modern science data analysis. Before we move on to an overview of how data science can help, let's first spend some time removing jargon barriers and defining our scope. As SUDS is fundamentally a community building activity between 6 distinct cultures, language can matter a great deal. My goal is to rapidly introduce some useful data science nomenclature and concepts to facilitate collaboration, while avoiding getting into ideological debates. Data science has many application areas, each defined by their unique goals and typical approaches. As an example, let's consider the context of a fairly standard science data mission pipeline here at JPL. First, the data must be calibrated and processed before it's ready for investigation. The algorithms involved can be complex and computationally intensive, such as physical models or iterative inverse problems. Data science can play a role in accelerating these pipelines, but that's not the goal of SUDS. Once the processed data is in the hands of the physical scientist, the main thrust of SUDS begins. A variety of manual, often painful to repeat processes commence. The goal is insight generation. Directly helping the physical scientist achieve this goal is the heart of the SUDS endeavor. Beyond this, analysis results may have downstream decisional impact, such as research decisions to alter and improve physical models, mission decisions, like whether a data version is ready for public release, mission ops planning decisions, or even further to societal decisions and policymaking. Let's call out 4 application areas as they relate to SUDS. Automation is defined by creating an algorithm that happens the same way every time on all data. Working with a data scientist on automation can help reduce random biases and manual procedures and characterize the biases that remain. There is minor SUDS overlap with automation, as data scientists often initially work with a physical scientist to help automate their investigations as a first step of the collaboration. Emulation replaces a slow model with a faster data science version. You'd only do this if you can't afford to just run the original model for some reason, often derived by the need for ensemble studies for sensitivity, optimization, uncertainty quantification, or to meet real-time requirements. SUDS isn't about emulation, but some emulation work can enable new SUDS outcomes, as we'll see. Autonomy is separate from, but can involve data science approaches, and is defined by actually making decisions normally reserved for humans, not just automation. While there are onboard science autonomy applications that support SUDS by capturing science phenomenon otherwise out of our reach, SUDS is otherwise distinct from autonomy. Furthering our understanding is what SUDS is about, using data science for the purpose of insight generation. To drive this distinction home, we may in fact discard our models after our conclusions are substantiated. This isn't a software or model delivery goal, and it's not a technology push. It's knowledge and insight co-generation. The SUDS effort exists within JPL among many closely aligned interests. Mission formulation and strong traceable proposal concepts can benefit from data science approaches, especially uncertainty quantification and emulation. The natural way data science can enable fusion of science and non-science datasets informs science applications and decision makers. Onboard science capture of changing or transient events, as well as the prioritization and summarization of high-volume science instruments, often involves data science approaches. And finally, data science can have a role to play in optimizing and accelerating science data pipelines. These four areas are allied with but distinct from SUDS. Our focus on understanding is our uniqueness. And since approaches that facilitate understanding are usually also desirable, SUDS approaches can inform and produce significant cross-cutting impact. So in a nutshell, what's so different about modern data science approaches compared to traditional analysis? One useful difference is captured by the concept of data-driven, where structures in the data take on a guiding role to help speed understanding. To illustrate, let's first define an idealized cartoon of the conventional analysis workflow. A physical scientist may have at their disposal a physical model, capturing the current theoretical understanding, abundant observations, and by comparing the residual errors where they disagree. The researcher analyzes and reasons about these residuals, formulating multiple hypotheses to check. Note that the hypotheses came from the researcher. These hypotheses are then tested or confirmed on the relevant subsets of the data, and if they are confirmed, may result in insight. When sufficient insight is reached, the researcher may choose to update their physical model, and so the cycle continues. This works. This is good. It got us to the moon, and it isn't going anywhere. But what's new? A different way to proceed that can augment the traditional approach. In this approach, physical science intuition is engaged to ask high-level questions of the data, rather than formulate low-level explanations. This is what data-driven means. Examples include, how many kinds of observations are there? Can this subset of variables predict another subset? Are there more events that look like this one? Translated into data science approaches, these high-level questions can be answered consistently with all of the data at much larger scales. The statistical approaches here aren't focused on confirming a hypothesis, but rather on facilitating exploration and discovery. Data science springs to work, producing fast statistical models that capture relevant hidden data structures and relationships. We didn't construct these manually. They were made for us from the data itself by the questions we asked. Now, the key SUDS moment. The validated models can then be mined to produce candidate hypotheses that augment and inform the researcher's conventional investigation. The researcher gets hints by looking at the data from these new directions. Sometimes the explanatory models also perform a useful action and might be exported to enable automation or autonomy applications. And that's why there's sometimes confusion over these terms, but that isn't the point. The concept here is that a data-driven approach can be a second pathway to produce insight that leverages powerful exploratory statistical modeling. It requires less initial upfront theoretical understanding by exposing the relationships and structures within the data itself. But in the end, traditional analysis usually returns to confirm valid conclusions. Now let's define a primary SUDS challenge to data-driven approaches, that of a model-rich environment. A typical data-driven problem formulation, say using machine learning, requires input and output data, a choice of a goal metric, and a validation plan. In return, machine learning creates a statistical model for you that maps the input to the output. But physical science often already has existing models in abundance. These may be detailed first principles simulations, statistical climatology, or assimilative models. The challenge of formulating data-driven approaches so that they leverage rather than ignore existing models is called data science in a model-rich environment and forms a cutting-edge research field. The goal is to ensure you don't waste time rediscovering what you already knew. Lastly, let's consider a thorny question that always arises during data-driven formulation. How much data do I need to provide to build my model? Or phrased better, which data do I need to provide to build my model? There's no simple answer to this question, but there are best practices to help identify when you don't have enough, and deep peril when you don't have those practices in place. You see, data-driven models excel because they find the shortest path from the input data to the desired output. This can be a big win for computational efficiency and revealing unexpected relationships, but it can also result in cheating. For example, let's take the case of machine learning to estimate tree canopy height directly from complex SAR data, with a truth source measured by collected LiDAR observations. This is a well-formed proposition, and several researchers at JPL are actually exploring this exact goal right now. However, I've changed the details to protect the innocent in this example. After model training, initial results are highly encouraging, and while the accuracy isn't yet at the needed level, there are plenty of model adjustments to try. But as the project goes on, tweaking the model doesn't seem to be improving the accuracy at all. The problem is revealed in the training data itself. Samples were taken from 3 disparate locations in 3 different kinds of forest, with very similar canopy heights within each forest and very different heights between the forests. The shortest path for the model was to predict only which forest I'm currently in based on the SAR data, and then just guess the average height of that forest. Not at all we were hoping for. And clearly here, 70% accuracy actually defines a baseline of no meaningful predictive skill. This example emphasizes the critical role that exploratory data analysis plays before and after engaging data-driven approaches, as well as a thoughtful validation plan that protects against leveraging irrelevant correlations by asking the right questions up front. Average accuracy isn't usually even close to sufficient when the goal is understanding. Armed with our new data science vocabulary, let's proceed with a broad overview of the understanding-focused capabilities data science brings to physical science analysis. As we proceed, see if you can identify where some of your own SUDS needs or past experience might fall. You'll also note that I say at the top, how can we help each other? I mean this quite literally, because the needs of physical science inquiry also form some of the most interesting data science research challenges that I know. It's fruitful to discuss how data science supports physical science differently, depending on the science field maturity. Most fields begin with continuous data records of observation awaiting exploration and understanding. These not need be imagery, but may be multivariate time series, spectra, or any other undifferentiated observational record that has yet to be tamed, as it were. The next step of maturity is often to categorize and gather similar events or regions. Let's call this the catalog phase, defined by the boundaries between and characterization of its contents. This can't happen until there are abundant examples of each type of interest. The next step involves theoretical modeling of specific catalog entry types, translating observation to explanation. This doesn't proceed evenly, with common events likely understood first and rare events lagging. This step requires sufficient theory to build and validate explanatory models. One next step may be to connect these models in an integrated system simulation capability. The focus then is to verify consistency between components, gap analysis of what's still missing, and detailed interpretation of the larger scale past and present. Finally, full-scale models become assimilative observational systems, ingesting real-time data from multiple sources and providing skilled multi-scale predictions of the past, present, and future. Each science subdomain, for example, Earth's atmosphere versus the Martian surface above, is at a very different point in this journey of understanding. So how can data science help each of these phases? In the continuum record, data-driven discovery techniques can help initially define and populate the catalog entries. Once a catalog exists, data science comes into its own by accelerating the growth, purification, and characterization of its contents, as well as facilitating the capture and representation of physical science insight to inform the broader community. As theoretical understanding grows, purely data-driven approaches inspire and inform candidate hypotheses, then shift to help evaluate and rigorously test theoretical predictions. In the regime of global models, data science facilitates the translation of model error into further insight, as well as enabling computational efficiency where necessary. Finally, in the most mature phases, data science centers around decisional support through data fusion, rigorous uncertainty quantification, and computational efficiency for operational systems. Each science subdomain is somewhere on this journey, and SUDS will apply differently based on the current needs. Now let's zoom in on these approaches that facilitate first the catalog phase of science understanding. Catalogs may be initially constructed from any kind of science observation and by many criteria. For example, we may specify planetary surface features of interest such as craters, spatial regions undergoing rapid change such as deforestation. We may capture unusual or extreme examples different from the rest of the record, or events that are most surprising based on what came temporally before. We could identify and sample the most representative regions, or those that most disagree with model prediction. This initial catalog construction is a uniquely important time in a SUDS collaboration, while here we have a chance to encode much of our expert understanding and intuition in the kinds of information we extract from and add to our examples. We make note of any useful context that may later be helpful, such as location, season, terrain type, data quality, and even human judgments or descriptions like star-shaped or sandy. Additional data sets can be co-located and added as well, enriching the catalog record and deepening its potential for later insight. Once we have an initial catalog, the real fun begins. We can engage in two fundamental activities, one that seeks to grow the catalog larger and the other that seeks to understand what we have. This is iterative knowledge capture and co-generation, and it can be fundamental to the support of open science. To grow the catalog, we return to the vastly larger, yet to be cataloged observational record. Data science allows us to search the raw data by similarity to existing entries, such as find more things like this, or by dissimilarity, seeking examples that have no current overlap. Further, we may seek confused items that seem to belong to multiple categories and may form important boundaries. Once our catalog is large enough, we then turn to understanding what we have. We can look for emergent structure and groups that we didn't encode into the catalogs ourselves. We can seek outliers and anomalies, or identify that some of our categorizations have meaningful subcategories that require reorganization. As we have them, we may bring in theoretical models for comparison, and where we find disagreement or surprising behavior, ensure that we didn't make mistakes during the initial catalog formation. Finally, we close on this phase SUDS goal, to facilitate the characterization of structure within similar catalog entries, identification of discriminating features, and capture of expert insight and knowledge into annotations to inform later studies. The pure data science nomenclature for this entire process is simply making a labeled dataset. But for SUDS, a more productive perspective may be that you are starting to create an analysis-ready catalog as a growing community resource. Initial efforts that plan and welcome iterative growth phases with multiple users, the capture of multiple annotations for each item by different experts, the capture of additional metadata or attributions that may later prove informative, early adoption of uncertainty awareness, and leveraging standard user interfaces and data formats are all guiding principles that can significantly increase SUDS catalog productivity. Finally, as physical insights are obtained, put them back in the catalog so that others may continue to benefit and build on them. Now, let's move on to the next notional science phase, where we're comparing physical models to our observations. Data science can help shed light on where and why our models continue to make errors. The process is similar to a sensitivity study, but instead focuses on which data best predicts the errors. As a concrete example, let's consider a typical atmospheric mission retrieval scenario, where input spectra are transformed by physical model inference into atmospheric parameter estimates, such as for the OCO2 mission. By comparing these atmospheric parameters where we have independent truth, we calculate the residual error from our model. To prepare for the application of data science to derive insight from these errors, we gather all the candidate information that might be useful. We have thousands of variables within the complex input radiance spectra themselves, one per wavelength. We have hundreds of statistics from the physical model's operation, such as fit coefficients, covariances, and averaging kernels. In addition, we're allowed to bring in any other information that might be useful, such as observation geometry, co-located data from other sources, such as weather, or even the output of alternative models. Now, using any and all of the potential informative variables, use machine learning to quickly train a model to predict the retrieved error on the residuals, the thing that we want to reduce. Here's the first key concept. If our model shows any skill at predicting the residuals, even incompletely, that means it has captured a potentially insightful relationship that characterizes those errors. And with the right setup, we can interrogate that model to identify the handful of variables that best predicts our original retrieval's error. Out of the hundreds or thousands of variables this process suggests, consider these first. They matter most. And here's how much of your error they explain. That can be a big help when you're trying to diagnose a complex model in a complex environment. As a concrete example, this exact analysis was done for the OCO2 early mission phase, and some of the predictive variables it uncovered revealed an actual coding error in the representation of high icy clouds in the physical model itself. Now let's talk about a purely data-driven alternative to model-based inference. Humans are visual thinkers, and often if we could just discover the right data combinations and transformations to graph, some meaning would become clear. That's where dimensionality reduction and clustering can help. These techniques directly confront and offer approaches to handle the challenges of highly dimensional data and its visualization. For example, a three-dimensional hyperspectral image stack, such as the SPG mission will produce, is like a normal RGB image, except with hundreds or thousands of colors, rather than three. This kind of data is challenging to visualize even as a single observation. One helpful data science technique seeks to extract a basis of a few end-member spectra that in combination and mixture explain the observed pixel diversity and form a smaller number of spectra for initial detailed analysis. Many scientists already employ a dimensionality reducing technique called principal component analysis, or PCA. PCA forms useful linear variable combinations that best capture the majority of the variation in a dataset. In this example, hurricane trajectories have been represented by 145 extracted parameters. That's not something one can easily compare, understand, or visualize. By using PCA and coloring by cluster, these highly dimensional trajectories could be arranged into a meaningful 3D space that provides hints at underlying common characteristics and furthers inquiry. In a last example, highly dimensional galactic spectra are fed into a neural network called a self-organizing map, or SOM, that learns a nonlinear mapping similar to PCA. The SOM attempts to minimize spectral differences between neighbors in that final two-dimensional visualized output space, arranging and rearranging the spectra until an optimum is found. By coloring the resulting map by a physically interpretable portion within the spectra, hints at physical interpretation of the captured relationships can be had. In all of these examples of dimensionality reduction, it's not about producing the one true representation of the data or confirming a specific hypothesis. Rather, it's about swiftly exploring and discovering useful transformations from the data itself that reveal tantalizing relationships for further investigation, as well as reducing the number of dimensions for later analyses. Now let's move on to later phases of science maturity. In scenarios where we might not yet have a detailed physical understanding of how inputs combine to predict a particularly complex or troublesome physical state parameter, we can use machine learning to directly probe the prediction feasibility by providing it access to many possible informative inputs, as we saw. Then, using the same key driver analysis as before, we can empirically determine the predictive subset of the inputs that mattered. This is especially important when ingesting or predicting very complex variables like estimated hurricane damage, socioeconomic data, or crop yields, where data relationships may still hold more information than our current theoretical understanding. This same problem setup is very flexible. For example, we can take a time series prediction problem and by feeding many samples from past data, construct a future predictor. This can be done for a single or very large numbers of variables simultaneously as input or output or both. Similarly, spatial context can be easily included for problems where nearby information may be informative, or space and time context together. The same key driver analysis applies here too, revealing the relative predictive power of local information versus spatial context versus temporal awareness. Predictors can also be designed to learn both predictive relationships and the averaging or interpolation that is needed. In this final example, we focus entirely on the learning of that interpolation. Here, we train a predictor with only space and time as input and ask it to reproduce our potentially noisy or gappy observations. By reducing the model order, choosing physically meaningful architectures, or regularizing based on information-based or physical constraints, the predictor can become a physics-informed interpolation scheme specific to your problem. Now let's move on to the mature science topic of how data-driven approaches can coexist with existing physical models, because it doesn't serve anyone to mine out insights from your data that you already knew. Here's the simplest way forward we've already seen, called data augmentation. We run the physical model as a preprocessor and train a corrector to catch any errors after the fact. The physical model is just another input variable to consider. This is easy to set up, easy to evaluate, and the correction model doesn't waste any time learning what the physical model already was getting right. One nice property is that even when you don't have an elaborate physical model, even a fairly simple one can help support the predictor in an interpretable manner. A totally different approach focuses on replacing only the computationally expensive or poorly represented sub-elements within an otherwise acceptable physical model. The resulting speedup can be fundamental to real-time pipeline applications, as well as enabling ensemble-based approaches for uncertainty quantification, sensitivity studies, and optimization. The conjugate of the previous approach attempts a fully data-driven prediction, but then seeks to constrain the learned model by known physics. These constraints could be at the highest coarses level, such as global conservation laws, or could involve detailed equations of state. By incorporating physical constraints, the data-driven learning problem is simplified, reducing the amount of training data required and extending the range of skilled prediction. There is significant current active research focused on expanding the potential of this approach. Lastly, the Holy Grail: to communicate data-driven results in the native language of physical science, that of symbolic differential equations. By constructing models that learn both the operators to apply to input data, such as time and space differentials, as well as how these terms are later combined into equations through relationships like sums and products, we may attempt to mine out new differential equation terms directly from the data and with respect to those we already know. This is early research, still discovering its potentials and limitations, so stay tuned. Our last overview topic for today is both highly promising and fraught with peril. My goal today is to equip you with the basic information to proceed safely and know how to avoid pitfalls. First, let's consider the case of gap-riddled data, say from a sensor that occasionally drops network packets. Gappy data is really horrible. It can severely limit downstream analysis by aliasing longer scale structures, and many analyses frameworks and models won't even be able to ingest it. Using a technique called inpainting, a data-driven model can be constructed to predict the missing values based on the past, other related co-observations in the present, and physical constraints. Done correctly, this approach estimates the missing data. Keep that core concept for a moment. We'll never know what the missing data really was, but we can sometimes estimate it. The second case is called upscaling and pertains to when we wish to estimate a higher resolution product from a lower resolution one. Again, a data-driven model can be trained to ingest a low resolution observation, combine it with related high resolution information, and produce an estimate of the high resolution version of the input observation. You've heard me emphasize the word estimate several times, and that's the key to remain safe. If you treat the output of these models like any other estimate, you immediately understand that their results are only to be trusted as far as they have been rigorously validated. And one would never wish downstream users to be confused whether each observation was an original raw value or the results of an estimation procedure. This is absolutely not magical information from nothing. It's just an estimation problem that relies on structures within the original inputs and these green boxes of additional information. So where's the peril? Keep your eyes on the green stuff. The peril is that if you remove these green boxes, the procedure still seems to work, dangerously like magic. What's going on is that the data-driven models faced only with the data that they have, be it gappy or low resolution, attempt to solve the problem you presented by learning the most likely, most plausible structures to fill in. This does not mean at all that this is really what belongs there. But what's worse is that the models likely won't do something foolish or easily spotted, like a crude average or blur that we could see. Rather, they will fill in the gaps and augment the resolution with highly realistic looking contents that respect many of the structures in the rest of the data that an expert might use to verify. In essence, with powerful enough models, we can construct highly believable but entirely erroneous science data products. This is the threat of deepfake science data. And while you don't need data science to achieve it, data science can produce it by accident if you're not careful. To drive this home, consider the same technology in one of its original forms, to add color to black and white movies seemingly from nothing. Science is often about finding the strange or unlikely thing, not assuming the plausible or expected. You'd never guess a pink beard if you've rarely ever seen one. So what should caution look like here? Ensuring independent truth is available for validation at the higher resolution or within the predicted gaps. Good old-fashioned cross-validation, and embracing uncertainty quantification as a warning for downstream users to what the variation could be for the estimates. Despite these reasonable suggestions, I see multiple proposals a year present these frameworks like the ones before you now. As we build the SUDS community together, let's make sure that everyone gets the opportunity to learn not only powerful data science capabilities, but also the rigor to use them wisely. Thank you for your time and attention today, and hopefully this has left you with a thirst for more. Every month, the SUDS community building efforts will be providing educational and training opportunities, useful services and resources for engagement and collaboration, and inspiring examples within and beyond JPL through our seminar series and Trailblazing initiative. We look very forward to meeting and engaging with you all, be it an email, WebEx, on our community Slack channel, or hopefully one day soon in person. Thank you very much.
Thank you, Lucas. That was great.
We have some questions in the chat.
I think we have one question and it was deemed answered. I will just say that we purposely are intending this seminar series to leave room for questions and answers. And Amy Braverman, you have a question.
Yeah, Lucas, terrific talk, by the way. You're a star. You're my hero. I do have to say that my insecure statistician kind of pops up a little bit at the idea of suggesting that ML is sort of this all-purpose Swiss Army knife of things that can do things like gap filling and upscaling, downscaling, and then sort of glomming onto the back end of that the idea that uncertainty quantification can help you decide how much to rely on that. And that is true. I mean, you could partition the problem that way, but I'd also like to suggest that the term ML, perhaps you mean it kind of broadly to include probabilistically based modeling, because machine learning algorithms, as they're sort of generally understood, right, as they sort of exist in the literature, are not typically probabilistically based. There are some instances where there are sort of things based on Bayesian methods and things like that, but the notion of in spatial statistics, we formulate specific probability models that describe the relationships among observations at different locations, for example, or at different resolutions. And that comes with a built-in uncertainty measure because it's based on a probability model. So it is certainly still data science, no question about that. But I do want to point out that using ML to make these predictions and then approaching uncertainty quantification after the fact is not the only way to do it.
So let me first completely embrace what you say. I absolutely agree. In fact, the reason that I showed that last example is not because I'm trying to say this is the one correct way it should be done, but rather I am seeing people do it this way, and I want them to be aware of what would be required if they approached that way. How I would differentiate the different approaches that you just identified is if you have a deep understanding of those initial distributions and the relationships, it is most likely useful to proceed in what I would call the forward traditional statistical way. We know the distributions, we know the relationships, we know their uncertainties, we proceed forward. If we do not know those and wish to try to mine it out of the data, it may be useful to consider a machine learning approach instead. However, it's not going to get you out of the weeds, because at the end, you now have to get an idea around that uncertainty again. So, and rather than trying to say ML is a run around it, I'm trying to actually embrace it and say uncertainty quantification is there no matter how you attack the problem. It just depends on if you want to do it right up front and have it baked in, or you're going to have to figure out how to bring it in at the end.
Agreed, although I would also like to point out that a big piece of spatial statistical modeling is estimating those probability structures. It's not like you have to come in with some specific idea in mind before you start. But I'm splitting hairs now, and like I said, I'm just being the insecure statistician in the face of all the sexiness of machine learning. So,
well, let me embrace that insecurity and say rather, I adore the rigor, and let's do this together.
Yeah, and I'd also like to make one other point that I think you did make, but I feel like you didn't emphasize it enough, which is that the research synergy between the science problems and the data science approaches is really important here, and that's where we at JPL are in a unique position to develop this. There aren't too many places around the world that have data scientists and physical scientists in such close and constant proximity to one another, where new data science research is stimulated by science problems and new science insights can arise based on the application of new data science techniques coupled with the science. So I think that is super important for JPL and unique to JPL in many ways.
Full agreement. Yeah, I actually do think we are a world leader in this area.
Yeah. And part of the goal of this seminar will also be to get some of the different science disciplines at JPL that might have what appears to be very different physical science questions, but from the data science side, they're similar, of finding the outliers in a galaxy catalog or finding the hurricane. Or now we have one very quick question from Nikita Kamraj. When will the data science short courses launch, and how do we register for them?
So currently they are being developed and are there are hackathon experiences for you to be able to play with data science, and there are short courses both to introduce physical science domain areas to help educate the data scientists and data science concepts to help educate physical scientists. We are in our trial phase right now, and in the February-March timeframe, we plan to actually have some public announcements when these come out. The short courses will be able to host a large number of people. The hackathons will have to be a more curated experience based on their nature. But these announcements will be coming out in JPL space and also through Slack and the email, as long as you have joined the community, the SUDS community. And if you haven't yet, please reach out to us and we're happy to make those connections.
Gilberto.
Gilberto Vicente from NASA Goddard. I work at the DAC, the Data Active Archive Center, for many, many years as this. And during that time, I interacted with the eCIP organizations, and we were very concerned about format, about having the data in one place or having the data distributed in many, many places. And we always had the issue of how to make all those things talk to each other, how to take advantage of them, not reinventing the same thing over and over again. So what I see now is this initiative is pretty interesting. I like your presentation, very complete. But again, I have the same concerns I had in the past, which is how can you make this not another project like many that we already have? How are we going to use things like, for example, the cloud? Because you are dealing with a tremendous amount of data. And then, like, for example, how is your plan to set a platform so that this is just not a series of workshops and training, so that people who actually have a place where they can go and they can access the data that is distributed in many parts in the country, and then have the tools to grab that data in a format that they can use, combine them, and put them to work on whatever problems they have. Like, what standards are you proposing? How are you setting the structure for this? Because I'm looking at on the long term and how this will be actually useful for the scientist that does not want to study data science and learn about those things. How can you create tools that someone who doesn't know as much as data can use the information to do their work and stay being a physical scientist? Don't force people to be data scientists. Can you address that?
I can, and what you are addressing is an entire leg of data science that I explicitly did not address here, which I would call the infrastructure and support needed to be able to do all these things. So this is scalable computing, data transport, all those things, putting your compute to the data, edge computing, all that stuff, clouds. And there are other initiatives at JPL that are looking at these aspects of the problem. SUDS was created because no one was looking specifically at assisting the scientists to look at complex data. So while big data is part of our journey, it is not one of the key drivers of what we're trying to develop right now. It is instead our ally that we will be working with. But the platforms and others, there are others at JPL I can get you in connection with that are engaging that aspect of the problem, both for science data processing as well as research analysis.
Great. Maybe there's a question from Kyung Sung in the chat. Kyung, do you want to bring it to the floor, or I'll give you that?
Okay,
chance.
yeah, let me go ahead. Yeah, thank you very much. It's an amazing talk. We have a laboratory spectrum from which we try to determine the line parameter, position, intensity, line width, and so on. Thus, we have a very well-defined Ford model, and we also use inverse model. Suppose one spectral line is characterized by 5 line parameters for given 5 global parameters shared by all lines captured. Do you think one can achieve precision accuracy to 1% level for these line parameters using this approach?
That would not be a precision question I would want to answer off the cuff here. I would definitely need to sit down with you and look at the problem more.
Okay.
Yeah, that's very specific.
Okay.
Maybe that leads to a very natural next question. How can data scientists and scientists collaborate?
That is a great question. I would say that a useful framework is first for the data scientist to sit down and listen to what are the current pain points? What are the challenges? What's not working? Because there's no reason to reproduce anything that is. The next is to gather the necessary context. What papers need to be read? What understanding of the physical science domain needs to be incorporated to the data scientists so that they can understand? The third step then is to actually share some of your data with the data scientist, because this is not just preparing them to address your problem, but they are now bringing their intuition, their experience and insights into the character of the data itself. From that, they will generate a wonderful series of questions that should create a useful dialogue. That dialogue begins to grow. And slowly, the pain point and challenge that the physical scientist had is converted into several potential data science frameworks that can go forward to address it. Each one of those is then chosen, described by useful metrics, and one is pursued. And the most important step is to allocate plentiful time at the end on how to map those results back into physical understanding. In research tasks, that is usually given too little time, but actually involves quite a lot of work, and even other data science approaches to help gain insight into the results of the first data science approach. I would say that is a general framework of going forward.
And as you can see from the slide that's up right now, SUDS is envisioning this multi-pronged attack to really build this data scientist community at JPL. And Lukas is the lead of that first screen box, informal consultation.
That actually is an error. That's supposed to say in transition. I apologize for that. We fixed that in one place, not the other.
Okay.
So there will be a working group lead for informal consultation, which will be bringing forward groups of data scientists who like to do exactly what we just talked about. I apologize for that error on the slide.
Can I ask a question, Daniel?
Yeah.
Hi, this is Fred. Hi, Luke. So I have a question in terms of where do you put the data science effort? Is it better to have your data scientist working with scientists, or how much should you be training physical scientists in data science techniques? I know there's there's a sliding scale there depending on who you're talking to, but it seems like there's a point where it's not just having the physical scientists work with the data scientists, but actually teaching them how to do data science, at least to some level, so then they know how to ask the right questions for the next level, which is like, well, I did this analysis, but I need to do more. Can you help me?
That is a fantastic question, and I definitely have answers for you. It is very analogous to computer modeling and simulation. There are some physical scientists who become quite enamored of this field and become highly proficient, excellent data scientists in their own right. And then, of course, they have their deep physical intuition as well from their science side, and they proceed forward in that way. There are others who are embracing the physical science aspect and perhaps do not want to allocate that much of their time to acquire deep research grade data science, but they can still become practitioners of data science tools and techniques. But then, as you say, they can enter into a certain depth and may also recognize when their depth has exceeded and want to bring in research grade data scientists to collaborate and formulate better approaches and see what's going on. In a similar way that you would reach out to a researcher to change a computer model or build a new one. I will also answer your question by saying that there are two flavors of research grade data scientists. One will become enamored of a particular physical science area and themselves acquire very deep understanding of the typical data sets, the questions, and the area. They will somewhat specialize, and that's valuable. However, there is a very real hybrid vigor, it is called, a cross-cutting capability that by working on multiple different science areas, a data scientist can build useful intuition that can transition technology from one area to another or bring useful, new, fresh ideas. So we actually need all three of those in play. We need physical scientists to be comfortable with these tools to the level that they choose and to be able to recognize what does it look like if they need more support. We need specialists that they can talk to that have one leg in their area and one leg in the data science and specialize with their understanding of that. And then we need some of those experts in the cross-cutting hybridization to bring in fresh ideas and support. And they also, that last group, forms the standards and upgrades the concept of data science itself. What are the new ways we should be doing it? What are the better solutions overall? How are we going to advance this as a science itself? And then that has a trickle-down effect to everyone else. So we need all three of these populations in the end functioning in our community.
Great, Lukas. We just hit the hour. I want to thank Lukas once again for giving an amazing talk and a great introduction to the SUDS seminar. Next month, we will be hearing from Alex Gardner, who will do a deep dive into one sort of method of data science and a specific question, namely Gaussian processes for understanding ice sheets. Look out, that'll be March 1st. It'll be well announced ahead of time. And if people want to stay after the seminar's working group, I'm inviting them to stay after just to do sort of lessons learned from this first seminar, but anyone who wants to stay on is welcome to, and we're just kind of we're trying to make this seminar as useful as possible. So thank you one more time to Lukas, and we'll start that after talk in a minute or two.
Thanks, everyone.
Thank you, Lukas. Thank you, Daniel. I will stop the recording. That's okay.